This is part 9 of the Module 9 lecture. In this part, we're going to introduce the comparing the mean of two paired samples. This is discussed in the section 10.4 of your textbook. Now, looking at this flow diagram that is been using to guide the discussion in this Module 9, you can see that in terms of independent populations, we have discussed the comparison of the variances, the comparisons of the means when the variances are equal, and the comparisons of the means when the variances are not equal. Now, in this situation, we're going to talk about dependent samples. And here is where we look at the comparison of the mean of the differences of the paired samples and versus some constant. All right, so we're going to talk about this here, the idea of dependent samples. Now, let's look at an example to see how this works. So in this example, a research institution claims that the IQ of children with mild autism that are subjected to some intensive multimodal methodology, this is some sort of a special training, increases the IQ of these children on average by 20 points. So a researcher, skeptical of this claim, wants to verify this. So for that purpose, this person performs an experiment where 31 children with mild autism are selected at random. Then once they have the children selected, they measure their IQ, and then they subject them to this multimodal training. And once they go through the multimodal training, at the end, they measure their IQ again. So this is a clear case of related samples. You may say, why? Well, because the sample is of 31 children. And so the children are measured before and after this training. So it's the same subjects from the same population, but they are measured at two instances or after some intervention. So these samples are related, and they are related by the individual on which the measurements are taken. So in this case, you can see that the results of an experiment like this, you will see two columns, the IQ before the training and the IQ after the training. Now, trying to compare the mean of the IQ before with the mean of the IQ after, well, that's not a good idea, because that will be like treating this as if they were samples from independent populations, and that is not correct. And the worst part is that by doing that, you ignore the effect of each child, or rather the effect of the training on each of the children, because some children will benefit more than others, and by ignoring that fact, then the variability of your data is going to increase, and it is going to be less likely that you detect a difference between the two groups. So treating this as independent samples from independent populations is not correct. The better approach, and what we call the correct approach, is to take the difference between the observations before and after, and then analyze those differences. So we call this difference, we use the letter D to designate the difference between the observation, in this case, after minus before. And you see here the gains in IQ before and after the training. And so what we do then is we make inferences about the population mean of the differences of the two observations for each subject. And so we're going to call that mu sub D. With that in mind, then, you see that we have a new variable, and we're going to call it D for the difference of the two observations of each member in the population. And then the mean of those differences, we're going to call it mu sub D, and the standard deviation of the population of difference, we're going to call it sigma sub D. Now, in order to estimate these parameters, we use this formula, the same that we use in Module 3, except that instead of calling it X bar, now we're calling it D bar. D to emphasize the fact that these come from the differences. So D bar is the sum of the difference divided by the number of differences. And to calculate the standard deviation of the difference, we use the same formula we use in Module 3. All right, so now this is telling you we're dealing with a single population of differences. So we're not dealing with two populations anymore, but with a single population of differences. All right, so to make an inference about the population mean of the differences, we're going to rely on the sample mean of the differences. And for that, we need to use the sampling distribution of d bar. And so if these observations in the sample, the d's in the sample are independent, then you know that the mean of the sampling distribution of the average of difference is just mu sub d, and the standard deviation of the sampling distribution of d bar is just the standard deviation of the population of differences divided by the square root of the sample size. Now, if these differences come from a normal distribution, or the number of differences is larger than 30, then by the central limit theorem, you can claim that the sampling distribution of d bar is normal. So if you notice, I'm repeating what we did in Module 8. So it's pretty much the same thing. All right, so with that in mind, this is what I'm saying in this slide. So the problem of paired sample reduces to one population of differences, d, which is equivalent to what we discussed in Module 7 in terms of confidence intervals, and in Module 8 in terms of the hypothesis test of a single population mean. All right, and the procedure that we're going to follow to test the hypothesis is exactly the same as before. And in fact, what we're going to do next is exactly what we did in Module 8. So to the hypothesis, when you have a two-tailed test, now we said that the mean of the difference is equal to 0 versus the mean of the difference not being 0. Now, you need to be careful. There are problems where someone is claimed that this difference is other than 0. They may want to show that the difference between the two samples is, not equal to 20. So in that case, you don't use 0, you will use 20. So you need to read the problem carefully and ensure that whether they're evaluating a difference of 0 or a difference other than 0. Now, if you have a left-tailed test, then you would expect the mean of the difference to be less, in this particular case, less than 0, because that's a left-tailed test, or the mean of difference is bigger than 0 in the case that you have a right-tailed test. And of course, here's the null hypothesis for the left-tailed test, and here's the null hypothesis for the right-tailed test. All right, so we're stating the hypothesis in the same way that we did in Module 8. All right, the test statistic, again, we do not know the variance of the population of differences. So we're going to use the sample estimate, S sub d, of these differences, and we're going to replace it into the test statistic. So now the test statistic is defined as the sample average of differences from the sample minus the mean of the differences from the null hypothesis divided by the standard deviation of the differences, dividing that by the square root of the number of differences. Now, if the differences in the samples are independent and the sampling distribution of d bar is normal, either because these come from a normal distribution or the sample size is bigger than 30, then this test statistic follows a t distribution with degrees of freedom equal to the number of differences minus 1. So again, this is the same definition of the t statistic or the test statistic as in Module 8. Now, if you decide to follow the critical value approach to test the null hypothesis, then the rejection regions are going to depend on the direction of the test. And to find the critical value that define the rejection region, we use table 5, which is the table of t probabilities, with the value of alpha and the degrees of freedom as the number of differences minus 1. So if you have a left-tailed test, then the rejection region is on the lower tail of the distribution. And if you have a right-tailed test, then the rejection region is on the right tail of the distribution. And if you have a two-tailed test, then you know that you divide alpha by 2 and you find the lower and upper critical values to define the lower and upper critical region. So this is exactly the same that we did in Module 8. So if you decide to use a critical value approach, then you will define your rejection regions as shown here. All right. Now, if you decide to follow the p-value approach, well, again, we follow the same rule as before. So if the p-value is smaller than alpha, we reject the null hypothesis. If the p-value is larger than alpha, then we do not reject the null hypothesis. And the p-value, again, is calculated based on the direction of the test. So if you have a left-tailed test, so the p-value is the probability of t less than the observed value of the statistic. And if you have a right-tailed test, so the p-value is the upper probability with respect to the t observed, the calculated value of the test statistic. And if you have a two-tailed test, then you multiply the probability to the right times 2, because you need to consider the probability on both tails. And again, I put the Excel formulas in case that you want to calculate the exact p-value. All right, so lastly, the definition of the confidence interval. This is exactly the same formulas that we have in Module 7, except that instead of using X bar, we use D bar, and we use the standard deviation of the differences and the square root of the number of differences. The T alpha over 2, again, is obtained from table 5 using the significance level and dividing it by 2, and then with the degrees of freedom of the T distribution. All right, so as you can see, we are pretty much repeating the formulas of the confidence interval, and is the same interpretation as in Module 7. When it comes to test the hypothesis, then we're pretty much doing the same thing that we did in Module 8. All right, in the next section, we'll go through an example and see how this analysis is done. So I'm going to stop here now.